Section 10.2, mass and the mole. Relate the mass of an atom to the mass of a mole of atoms. Convert between number of moles and the mass of an element. Convert between number of moles and number of atoms of an element. Some vocabulary review will be conversion factor, and some new vocabulary you'll come across is molar mass. You would not expect a dozen limes to have the same mass as a dozen eggs. Because eggs and limes differ in size and composition, it is not surprising that they have different masses. 1 mole quantity of different substances have different masses for the same reason. The substances have different compositions. For example, if you were to put 1 mole of carbon and 1 mole of copper on separate balances, you would see a difference in mass, just as you would see with the eggs and the limes. This occurs because carbon atoms differ from copper atoms. Thus, the mass of 6.02 times 10 to the 23rd carbon atoms does not equal the mass of 6.02 times 10 to the 23rd copper atoms. Recall from previous chapters that each atom of carbon-12 has a mass of 12 AMU. The atomic masses of all other elements are established relative to carbon-12. For example, an atom of hydrogen-1 has a mass of approximately 1 AMU, 1/12 the mass of carbon-12 atom. The mass of a helium atom, of helium-4, is approximately 4 AMUs, which is 1/3 the mass of a copper-12. You might have noticed, however, that the atomic mass values given on the periodic table are not exact integers. For example, you will find 12.011 AMUs for carbon, 1.008 AMUs for hydrogen, and 4.003 AMUs for helium. These non-integer values occur because they are values of weighted averages of the masses of all the naturally occurring isotopes of each element. How does the mass of one atom relate to the mass of 1 mole of that atom? Recall that the mole is defined as the number of carbon-12 atoms in exactly 12 grams of pure carbon. 12. Thus, the mass of 1 mole of carbon-12 atoms is 12 grams. Whether you're considering one single atom, or Avogadro's number of atoms, which we call a mole, the masses of all atoms are established relative to the mass of carbon-12. The mass in grams of 1 mole of any pure substance is called its molar mass. The molar mass of any element is numerically equal to its atomic mass, and it has the units G/mol, which is grams per mole. As given on the periodic table, an atom of iron has an atomic mass of 55.845 AMUs. Thus, the molar mass of iron is 54.845 grams per mole, and 1 mole, or 6.02 times 10 to the 23rd atoms of iron, has a mass of 55.845 grams. Note, by measuring 55.845 grams of iron, you indirectly count out 6.02 times 10 to the 23rd atoms of iron. And if you look at the figure of 1016, this will show you the relationship between iron and the number of atoms. So again, you can measure out a mole of iron on a scale, and when you measure that out on a scale, that would be the amount of atoms in which you have. And again, just to kind of keep it simple, instead of having to say Avogadro's number, you can always just say that it's 1 mole. So imagine your class brought jelly beans in bulk to sell by the dozen at a candy sale. You soon realize that it's way too much work to count out each dozen. So instead, you decide to measure the jelly beans by mass. You find that the mass of 1 dozen jelly beans is 35 grams. This relationship and the conversion factor that stem from it are as follows. That 1 dozen jelly beans is equal to 35 grams, And the two conversion factors you can get is 35 grams of jelly beans over a dozen, or a dozen over 35 grams of jelly beans. What mass of jelly beans should you measure if a customer wants 5 dozen? To determine this mass, you would multiply the number of dozen of jelly beans to be sold by the conversion factor. Select the conversion factor with the units you are converting to the numerator, which is grams, and the units in which you are converting from in the denominator, which is dozen. So we're going to go ahead and choose the first conversion factor so that they cancel out. So dozens cancel out. And that quantity of 5 dozens should have a mass of about 175 grams. Now suppose that while you're working in chemistry lab, you need 3 moles of copper for a chemical reaction. How would you measure that amount? Like 5 dozen jelly beans, the number of moles of copper can be converted to an equivalent mass and measured on a balance. To calculate the mass of a given number of moles, simply multiply the number of moles by the molar mass. Right? And again, if we needed to go ahead and find the molar mass of an element such as copper, what you're probably going to want to do is go to your periodic table. Right? At your periodic table, find whatever element that is you're looking for. In this case, it's going to be copper. Right? Copper, right here, number 29. And this has a mass of 63.546 AMUs, or grams per mole. Okay. Now you know the molar mass of an element, right? Could be in grams per mole, which is also equal to atomic mass units. Thus, copper has a molar mass of 63.546 grams per mole. By using this molar mass, you can convert 3 moles of copper to grams of copper. And again, we create a conversion factor that's so that the moles will cancel out, and that our conversion factor has moles in the denominator, and that we multiply the numerators together. So for 3 moles of copper, we would need to go ahead and measure out 191 grams. The reverse conversion factor from mass to moles also involves the molar mass as a conversion factor. Right? Just know when to use the one appropriately. All right, let's go ahead and look at example 10.2. All right, chromium, a transition element, is a component of a chrome plating. Chrome plating is used on metals and in steel alloys to control corrosion. Calculate the mass in grams of 0.0450 moles of chromium. Right, so when we analyze this problem, let's go ahead and recognize that you are given the number of moles of chromium and must convert it to an equivalent mass using the molar mass of chromium from the periodic table. Because the sample is less than 1/10 of a mole, the answer should be less than 1/10 of its molar mass. Right? That's just kind of a little tip there. So what we do know is the moles of chromium, and we do know the molar mass of chromium from our periodic table, but what we're looking for is the mass of chromium. So let's go ahead and use a conversion factor, right, the molar mass, that relates grams of chromium to the moles of chromium. Write the conversion factor with moles of chromium in the denominator and grams of chromium in the numerator. Substitute the known values in the equation and then solve. So we'll get at the moles here, and this what we're given. Then we want to set up a conversion factor so that moles will cancel because it's in the denominator. And when we do our arithmetic, it should cancel out and give us 2.34 grams of chromium. So let's go ahead and try practice problems 15A and 15B. So pause your video and give these a try. Here are your answers to 15A and 15B. If you examine the atomic mass values given on the periodic table, you will notice that the values differ in their number of significant figures. Most atomic mass values have 4 or 5 significant figures. When you use an atomic mass value from the periodic table, use all the significant figures provided. If your calculation involves several steps, do not round answers until the end of the calculation. By doing this, you increase the precision of any calculation involving atomic mass. Let's look at problem 10.3, a mass to mole conversion. Calcium, the 5th most abundant element on Earth, is always found combined with other elements because of its high reactivity. How many moles of calcium are in 525 grams of calcium? You must convert the mass of calcium to moles of calcium. The mass of calcium is more than 10 times larger than the molar mass. Therefore, the answer should be greater than 10 moles. We know that we're dealing with 525 grams of calcium, and we know that the molar mass of calcium is 40.08 grams per mole, and we found that from the periodic table. But what we don't know is the number of moles of calcium involved. So let's go ahead and use a conversion factor. In this case, it's going to be the inverse of molar mass that relates moles of calcium to grams of calcium. So let's go ahead and take 525 grams of calcium and multiply that by the conversion factor of 1 mole over the molar mass. All right. When you do your arithmetic, you should get something in the ballpark of 13.1 moles of calcium. All right, let's go ahead and take a second and pause the video and try practice problems 17A and 17B. Here are your answers to 17A and 17B. So far, you've learned how to convert mass to moles and moles to mass. You can go one step farther and convert mass to number of atoms. Recall that jelly beans you were selling at the candy store, at the candy sale. At the end of the day, you want to find that 550 grams of jelly beans is left unsold. Without counting, you can determine how many jelly beans that is. You know that 1 dozen jelly beans has a mass of 35 grams, and that 1 dozen is equal to 12 jelly beans. Thus, you can first convert the 550 grams to dozens of jelly beans by using the conversion factor that relates dozens and mass. Next, you can determine how many jelly beans are in 16 dozen by multiplying by the conversion factor that relates the number of particles, which are jelly beans, and dozens. The conversion factor relating number of jelly beans and dozens is 12 jelly beans per dozen. Applying it yields the answer in jelly beans. The 550 grams of jelly beans, of leftover jelly beans, is equal to 192 jelly beans. Just as you could not make a direct conversion from the mass of jelly beans to the number of jelly beans, you cannot make a direct conversion from the number of substance to the number of representative particles of that substance. You must convert mass to moles by multiplying by a conversion factor that relates moles and mass, and that conversion factor is the molar mass. The number of moles must then be multiplied by a conversion factor that relates the number of representative particles to moles. For this conversion, you will use Avogadro's number. Let's look at example 10.4. Mass to atoms conversions. Gold is one of a group of metals called the coinage metals, which consist of copper, silver, and gold. How many atoms of gold are in a U.S. Eagle, a gold alloy bullion with a mass of 31.1 grams of gold. Right, to analyze this problem, you must determine the number of atoms in a given mass of gold. Because you cannot convert directly from mass to the number of atoms, you must first convert the mass to moles using the molar mass. Then, convert moles to the number of atoms using Avogadro's number. The given mass of the gold coin is about 1/6 the molar mass of gold, which has about 196.97 grams per mole. And again, you can get that number right off your periodic table. So the number of gold atoms should be approximately 1/6 Avogadro's number. Some things that we know is the mass of gold in question, which is 31.1 grams, and we know the molar mass of gold. But what we do want to know is the number of atoms involved in that 31.1 grams. So what we're going to go ahead and do is use a conversion factor, right? In this case, the inverse of the molar mass, that relates moles of gold to grams of gold. So we're going to go ahead and convert that 31.1 grams to moles by using the conversion factor of 1 mole of gold over the molar mass. And that tells us how many moles, 0.158 moles of gold exist in that coin. Now we can take those moles and multiply it by Avogadro's number over 1 mole so that we can go ahead and find out how many atoms exist in that 31.1 grams, which turns out to be 9.51 times 10 to the 22nd atoms of gold. Just like we did a mass to atoms, we can also do a atoms to mass, and this is problem 10.5. Helium is an unreactive noble gas, often found in underground deposits mixed with methane. The mixture is separated by cooling the gaseous mixture until all but the helium has liquefied. A party balloon contains 5.50 times 10 to the 22nd atoms of helium gas. What is the mass in grams of the helium? So, to analyze this problem, you are given the number of atoms of helium and must find the mass of the gas. First, convert the number of atoms to moles, and then convert moles to grams. What we know is the number of atoms involved, and we also know the molar mass of helium, right, taken from the periodic table. What we don't know is the mass of the helium in our said balloon. We do know that in the balloon there are 5.50 times 10 to the 22nd atoms of helium. So let's convert those into moles of helium by multiplying that by 1 mole of helium over Avogadro's number. Now that we have the moles of helium, we can go ahead and relate that to mass by taking that moles of helium, the 0.0914, and multiplying that by the molar mass over 1 mole, which would tell us in that one given balloon we would have 0.366 grams of helium. So go ahead and pause your video and give practice problems 19A and 19B, as well as 20A and 20B a try. And here are your answers to 19A and B, as well as 20A and B. And instead of breaking down the conversion factors in different steps, I always like to go ahead and keep my calculations as precise as possible and just kind of carry through the dimensional analysis as I go. Notice how I kind of slash things here so that, you know, whatever it be a forward slash or a backward slash, they cancel out with the previous conversion factor. And if I have more, I kind of get creative. Instead of slashes, I might use X's or some squiggly lines. This is kind of how I do it. Now that you've practiced conversions between mass, moles, and representative particles, you probably realize that the mole is at the center of these calculations. Mass must always be converted to moles before being converted to atoms, and atoms must similarly be converted to moles before calculating their mass. Right? In Figure 10.8 shows a nice little flow chart to follow as you complete these conversions. In the example problems, 2 steps were used to convert either mass to moles to atoms or atoms to moles to mass. Instead of these 2 steps, these conversions can be made in 1 step. Suppose you want to find out how many atoms of oxygen are in 1 gram of oxygen. This calculation involves 2 conversions, mass to moles and then moles to atoms, which you can make in 1 equation. Right? I would definitely go ahead and make maybe a little flow chart that they have like this to keep in your notes. You know, going from mass to moles to representative particles, and representative particles to moles to mass. And just follow the arrows when you're doing this. Section 10.2 Summary. The mass in grams of 1 mole of any pure substance is called its molar mass. The molar mass of an element is numerically equal to its atomic mass. The molar mass of any substance is the mass in grams of Avogadro's number of representative particles of the substance. Molar mass is used to convert from moles to mass. The inverse of molar mass is used to convert from mass to moles.